Good afternoon, my dear friends. And in this video, we will solve 2018 GATE mathematics question paper. Okay, so let's begin. Here, you are required to find out the principal value of minus 1 to the power minus 2i over pi. Okay, so to solve this problem, you have got two ways, but we will consider the most simplest one. So whenever you get such kind of problem, try to solve this using Euler's identity. So just let me write down the Euler's identity. Okay, the solution here I'll be writing. Okay. The solution will be given by Euler's identity. Okay, what it has to say, it says that e power I is equal to cos z plus I over sin z. Well, this z is not complex number. It can be taken for any real. Okay, so in that case, we wanted to take minus 1. So in that purpose, what I put here at the place of z, that I get here minus 1. So simply if I put pi, okay, and that gives me here cos of pi, which is minus 1, and sin of pi is 0. So I got here minus 1. Now I need to find out minus 1 to the power minus 2 over pi. So I'll extend this quantity and get this e power I pi to the power minus of 2i over pi equals minus 1 to the power minus of 2i over pi. So that means I need to find out this value. So you seriously see pi and pi getting cancelled, and I into I will give me I square, which is minus 1. So you get simply e power minus 2 into minus 1, that is your minus 1 to the power minus 2i over pi, and it is nothing but e square. Okay, so your option A is correct. All right, now let's solve this one. Question number 2. What is there in question number 2? You are given an entire function with f of 0 1, f of 1 2, f dash 0 is 0, and it is saying that if there exists m such that this second derivative is bounded, okay, then what is f of 2? So to solve such kind of problem, you need to, mostly people think that it will be solved by using Liouville theorem, but there is a problem because here it is nowhere given that function is analytic. Entire is given, but there is nowhere it is written that function is bounded. Rather, they have given that the derivative is bounded. Okay, so we can't use Liouville theorem. Instead, we will just apply basic algebra and get it. Now, if you see very closely, then second derivative should be bounded by a natural number. Okay, m greater than 0. It can be real even, no problem. And it says that f dash 0 is 0. So I can construct a function. That means if I put 0, I should get 1. And if I at f of 1 equal to 2. So rather you can take f of z to be some a z square plus b. Okay. Such kind of function will be there. Now you want f of 0 to be 1. Okay, so f of 0 is 1. This implies what? If I put here 1, that gives me b. So I got b to be 1. And f dash 0 is 0. So let us differentiate this. Okay. Oh, wait. Oh, we have got one more condition. We've got one more thing. And if I apply f of 1, okay, 2. So that gives me 2 equal to a plus b. Also a is 1. Okay. Also 2 equal to a plus 1. So this implies a is again 1. Okay. So we see that we got our nice function f of z equal to z square plus 1. All we need to see just f dash 0 is 0 or not. So if you notice, then f dash z equals 2z, and at f dash 0 it is 0. So it's satisfied, and also f double dash z is 2, which is greater than 0. So this is your m. So we got this function f of z. Now what they want is f of 2. So f of 2 will be nothing but 5. Okay. So B option is correct. Now look at this. You are given a Lorentz series of 1 upon z over z minus 1 valid for mod of z minus 1 greater than 1. The coefficient of 1 upon z minus 1 is what? Okay, so we need to draw this disk, or we don't even need it. You want the coefficient of 1 upon z minus 1. So you can even apply residue theorem to find out this. Okay, or you may consider Lorentz series only. So let us consider the Lorentz series. So to do that, we have got f of z equals 1 over z minus 1. Now let's complete the partial fraction, and that gives me 1 over z minus 1 upon z. Is it true? Z minus 1 minus 1. Yeah, that's correct. So now it is given that the Lorentz series is valid for mod of z minus 1 greater than 1. So to apply the, basically we deal with geometric series here. So we know that, okay. So recall 1 over 1 minus z. What is that? 1 plus z square plus z cube and z power 4 and so on. And when you have a plus here, okay, so when you have plus 1 over 1 plus z, you get the same result except alternate plus minus sign. Rest everything will remain same. So our goal is to apply this, but to apply this we know that here mod of z is always less than 1, then we can apply. So here you are saying that mod of z minus 1 is greater than 1, so ultimately I have to make this quantity to be less than 1. So what should I do? Okay, can I do this? 1 greater than 1 upon mod z minus 1. Yeah, we got it. So that means we have to adjust this quantity. So for this term we don't have to worry about anything. So this will be kept as it is, and for this thing I'll just play a simple game. I'll add 1 and I'll subtract 1. Okay, and now in order to complete this thing, what I need to take 1 upon z minus 1 common. So I'll be getting here 1 plus 1 over z minus 1, right? And now if you expand this, so what you get, 1 over z minus 1 minus, this will be 1 over z minus 1 remain common, and expand this series now. So 1 minus 1 upon z minus 1, and then plus 1 upon z minus 1, yeah, and plus 1 over z minus 1 square minus 1 over z minus 1 cube and so on. And if you notice, then 1 over z minus 1 and minus 1 over z minus 1 plus 1 over z minus 1 square, okay, minus 1 over z minus 1 cube and so on. So this term gets cancelled. So there is no, okay, that means what? There is no term of 1 over z minus 1. So the coefficient is 0. So coefficient of 1 over z minus 1 is 0. So C option will be true. And if you look at the question number 4, then this is quite obvious and easy. It says that x and y are metric spaces. Okay, so let's take x and y to be the metric spaces. What it is saying, that f is a continuous map. So f is a continuous map from x to y. Okay, and for any subset of x, so let's take s to be a subset of x. Okay, s to be a subset of x, which of the following statement is true? It is saying that if s is open, then f of s is open. Well, at the first glance, you may think that by open mapping theorem, it is correct. Okay, if S is open, then f of S is open. But let me tell you, none of them are correct. Okay, except the connected thing. Because what we have learned isn't complex. And in real, the only thing which is correct is if the image here is open, then the inverse image is open. That means it sends the job, okay, of pulling. That means if V is open in Y, then F inverse V is open in X. So that's the true thing. If V is closed in Y, then F inverse V is closed in X. If V is bounded in Y, then F inverse of V is bounded in S. So the only thing is true for connected thing. Okay, so if the domain S here is connected and by a continuous map, then it takes connected sets to connected sets. So the B statement is true. Because this is open theorem. Okay, open theorem in the sense it's a closed. You consider it's a theorem, in fact, in your lower schools, bachelors. Okay, so please do not make any mistake while solving such kind of problem. You may end up having a wrong thing. Yeah, now consider this one. So you are given to solve the general solution of this differential equation. So let's consider this differential equation and solve it here. It's quite easy. So you are given that x y dash equals y plus under root x square plus y square. Can I divide by y dash? And that gives me y over x plus under root x square plus y square. And since this x I'm taking inside, so it will be x square. And now by looking at this, you might have got the idea that this is a homogeneous equation. So I'll put y by x to be v. So that is y equals to xv. So let us find out dy by dx. So dy by dx will be equal to x will remain here, dv over dx plus v will remain here, derivative of x is 1. So let us resubstitute in this equation, call this star and call this to be equation 1. Okay. So substituting in star, we get y dash is dy over dx, that is x dv over dx plus v equals v plus under root 1 plus v square. All right, so this v and this v gets vanished. Now this becomes a variable separable method. Okay, so this becomes a variable separable problem. So I'll just take this 1 plus v square term on this side and shift remaining terms there. So I get dx over x. Now the job will be to integrate this. And once I integrate this, I know that, okay, let me write down the formula in case you don't remember it. Okay, the formula goes like this. So I recall integral over 1 over x square plus a square dx is log of x plus under root x square plus a square plus c. Okay. This is the formula that we will be using here. So to do that, I'll just get log of v plus under root 1 plus v square equal to log x, and since these two terms are log, so I'll take log here k. Okay, now let's simplify the problem further. So that will give me log of v plus under root v square plus 1 minus log x will give me log k. And now by the property of logarithm, you get v plus under root v square plus 1 over x equal to k. No, sorry, log k. Okay, and in the very next term, okay, in the very next term, you can see this getting cancelled. We will get the exponentials. That gives me k. So I got v plus under root v square plus 1 equal to kx. And now let us resubstitute. Okay. So here we will now resubstitute the value of not the value, but it's v. Okay. So from here we get v to be y over x. So instead I'll put here y over x plus under root y square over x square plus 1 equal to kx. And now just take this x square out of this square root sign, so you get y plus under root y square plus x square over x equal to kx. Now so you get kx square equal to y plus under root x square plus y square. So that's my desired answer. And if you see, then it matches with the option kx square x plus, I think this should be the correct one. Okay. Yeah, it's y, kx square y. Okay. So C is the correct option. Okay. Now let's solve this one. So let P and X be the polynomial solution of the differential equation. Well, this given differential equation is legendary differential equation, and which is given in the compact form. So let us expand this form and write down the way it is. So the legendary equation is given by this. The derivative of is 1 minus 2x and then dy or dx plus n into n plus 1 into y equal to 0. And now you are given a recurrence relation. Okay, a recurrence relation is given by Pn plus 2 dash of x minus Pn dash of x equals to alpha n times Pn plus 1 of x. Then what is alpha n? Okay, so what is alpha n? That we need to find out. So the recurrence relation, okay, the recurrence relation of legendary equation is given by. So we know a recurrence relation, okay, in for the legendary differential equation, that is, I think this will work. 2n plus 1 into Pn of x equals, this is simply Pn plus 1 dash of x minus Pn minus 1 dash of x. And now let us consider here, if you see, then they have given n plus 2. So that means at the place of n, I have to take this recurrence relation for n plus 1. So in that case, I'll be getting here this quantity. Okay, that means, see, this worked for every n. So this should work for n plus 1 even. Okay, so for n equal to n plus 1. Okay, let us write down. So that will give me 2n plus 1 times Pn plus 1 x equals P n plus 1 dash of x minus Pn plus 1 minus 1 dash of x. So this 1 and 1 get cancelled. Now if you equate, you get 2n plus 3 over Pn plus 1 x equals Pn plus 2 dash of x and minus Pn dash of x. And if you compare the given relation with this thing, then this quantity right here is alpha n. So we get alpha n equals 2n plus 3. So we got alpha n to be 2n plus 3. In that case, D option is correct. All right, in that case, D option is correct. Now let's solve question number 7. What it says, in the permutation group S6, the number of elements of order 8. Okay, so such problems are quite easy. Remember to solve such trick. Okay, so just remember this result. In Sn, suppose you want to find out the number of elements of any order, any particular order. That means break this n. Okay, break this n in such a manner that if you take the, suppose you break n into n1 plus n2 plus n3 and so on up to some nm. Okay, you break this n, this 6. Okay, it should be broken in such a manner that if you get the LCM of n1, n2, n3 and so on up to nm, this should be equal to some k. Okay, the k is nothing but the order of element that you want. Okay, so now here you are given that in S6 you want the number of elements of order 8. So this will be our 6. So n is our 6. Okay, and k is our 8. That means we have to break 6 in such a manner that we get their LCM to be 8. Okay, we have to break 6 in such a way that we get the LCM 8. So is it possible? The partition for 6, I'll write down. Okay, you can write down here 6, you get 5 plus 1, you get here 2 plus 3. Start writing. Hold a moment. Yeah, sorry, something went wrong with this device. So I'm writing the partitions for 6. So here it is 6, and 5 plus 1 is also 6. 2 plus 3 plus 1 is also 6. And then 1 plus 1 plus 2 plus 1, 1, 2, 2, 4. And 2, 6. And then 1 plus 1 plus 1 plus 1 plus 2. 1 plus 1 plus 1 plus 1 plus 1. 3 plus 6. There will be one more partition, but in any way you are not getting LCM to be 8. Okay, because in S6 the maximum order. Okay, so you can write down here in S6 maximum order of an element. Okay, maximum order of an element is, just take the LCM. Okay, here you get LCM 5, here you get LCM 6, here you get LCM 2. So the maximum order is 6. Okay, so there will be, okay, so there will be no element of order 8. Okay, because in permutation group, you find the order of an element by taking the LCM of all disjoint cycles. So basically you have to break this n into the disjoint cycles and then take their LCM. So in case you break it and try to get LCM 8, then you won't be find any such partition. So there will be no element. So your option is A. Okay. And now look at this 9th problem. It says that f from R to R is a twice continuously differentiable function, the order of convergence of secant method. Okay. So this word itself is important, the order of convergence of secant method. So standard result is that order of convergence of secant method. Okay, so order of convergence of secant method is golden ratio. Okay, what is golden ratio? So that is 1.6180. Okay, and now if you're wondering what is this 1.6180, so you can simply solve this equation, that is x square equals to x plus 1. Okay, so you get x square minus x minus 1 equals 0. Now apply the Sridharacharya's formula. So you get 1 plus under root 1 plus 4 over 2. Okay, so you get 1 plus minus root 5 over 2. So you get 1 plus root 5 over 2 and 1 minus root 5 over 2. Well, this quantity is called as golden ratio, and this is conjugate golden ratio. Its value is 1.6180. So the answer is A option. And now, for a linear programming problem, which one of the following statement is false? Okay, they are asking which of the following is false. Now see, if a constraint is an inequality, then the corresponding dual variable is unrestricted in sign. That is correct. Okay, so that means suppose you get a problem, let's say maximize some C transpose into B, okay, such that your AX is equal to B. Then in the dual, okay, in the dual, the sign, the constraint, okay, that means let me not write down the B, let me write down capital B. So it will be here B transpose B, and then you get A transpose AX will be less than or equal to the corresponding. It will depend whether it is maximization or minimization. So here it is maximized, then it will be maximization, and then we have given this problem. So dual will be to minimize dual of this problem. Okay, this is the primal problem. Primal problem is to maximize, then the dual will be minimized. And if it is given equality, then in dual we have to minimize this problem. But since this was the equality constraint, so I'll have here equality constraint. Once again, minimize, no, yeah. So it will be greater than some what is here C, but the variable W, okay, in dual we get W. It will be unrestricted. It will be unrestricted. So this statement is true, and it is saying both primal and dual can be infeasible. Yes, even this is possible. Okay, so to solve such kind of problem, write down first what are true statements. So both primal and dual can be infeasible. Yes, that's correct. If the primal problem has infeasible solution, then dual has infeasible or unbounded solution. So that is fine. Now it is saying the same statement which I read just now. If primal is unbounded, then its dual is infeasible. Yeah, even that is correct. So these three options are correct. Now D is trivially false. Even if both and primal dual are feasible, the optimal values of primal and dual can differ, which is not possible because the optimal value and primal value, their values are same. Okay. It is saying it can differ, so it is not possible. So D option is false. Now consider problem number 13. What it has to say: you are given A equals some matrix, a symmetric matrix. So what they want is A, B, C, and F are real numbers. So the geometric multiplicity of the largest eigenvalues of A are. So since I'm not getting any idea, so for this purpose, I'll just take ABC to be just simply 1, 1, 1. Or better we take 0 and take F to be 1, okay? Because it is saying that ABC are a real number. So I can take any, so I'll take the easiest one. So A equal to 0, B equal to 0, and even take C equal to 0. And since F can't be 0, take F equal to 1. Okay. So we get a nice matrix which is 0, 2, 0, and 2, 0, 3, and 0, 3, 0. Now we can find out the eigenvalue of this matrix. Okay. And in case you want to find out the eigenvalue of this matrix, you just need to write down the characteristic polynomial. Okay. You just need to write down the characteristic polynomial and get that gives the result. So here you can get the characteristic polynomial. Okay. CH of x is, remember, lambda cube minus trace of this matrix times lambda square plus minus plus, and then sum of spatial minors times lambda plus minus plus, and then minus determinant of this matrix, okay, equal to 0. And if you noticed, then the determinant of this matrix will be 0. Okay, determinant of this matrix will be 0. You can notice even 0 into this quantity, so 2 into 0 will be 0 again, because this is an X matrix. Okay, this matrix is also called as X matrix. If all these elements here are 0, then the determinant of this matrix will be 0. Okay. Also, its eigenvalue I can tell you, but still we will solve it. Okay. 3 into 3, 9, plus 4, 13. Okay. So eigenvalue will be plus or minus root 13. Okay. Now let's watch out whether we get it or not. Let's see. So you get lambda cube minus trace of this matrix is 0. So you get, there will be no lambda square term. Sum of special minors. So special minors in the sense, you have to take the determinant of this matrix. So that is, it is plus now. So plus, it will be minus 4. And for this minor, I get minus 9. And the last corners one, it is completely 0. So there will be no minor. Now minus lambda and determinant is 0 equals 0. So I get lambda cube minus 13 lambda equal to 0. Take lambda common, so you get lambda square minus 13 equal to 0. Okay. So in that case, you get lambda equal to 0 and lambda equal to plus or minus root 13. Correct. So you got lambda equals 0, lambda equals root 13, and minus root 13. Okay. So since all the eigenvalues are distinct, okay, since all the eigenvalues are distinct, this implies matrix is diagonalizable. And even you can see by looking at the matrix, this is a symmetric matrix, so it is always diagonalizable. And if the matrix is diagonalizable, means its monic polynomial has, its a minimal polynomial has monic factors. So the AM and GM of every matrix will be same. Okay, so its AM is 1, AM is 1, AM is 1. So if the matrix is diagonalizable, so AM is same as GM. So the largest eigenvalue has GM 1, largest is 30, root 13. Okay, it has GM 1 because AM is again 1. So the answer here will be 1. All right. Now let's consider problem number 14. This is the same problem as solved in GATE 2017, except the thing that they were asking null space there, and right now here they have asked for the dimension of the subspace. So let's consider you are given that W1 equals collection of x1, x2, x3 belonging to R3, so that x1 is x2 plus 2 x3. Can I write it in this manner? X1 equal to, instead of x1, I'll write down x2 plus 2 x3 comma x2 comma x3. So I just have to check that how many vectors here are free. Okay. So, or either you can even find out the basis. So x2 is 1 here, and here it is also 1, 2, and here it is nothing. So 0 plus take x3 times, you get 2, 0, and 1. So that x2 comma x3 belong to set of reals. Now you can see that this is linear span of just only 2 vectors. Okay. 2, 0, and 1, and they are linearly independent. So dimension of W1 is 2. Okay. So dimension of W1 is 2. Similarly, you can find out the dimension of W2. Okay. Dimension of W2 also you will get 2. Or you are worried, then simply you can even apply this formula to find out the dimension rather than finding the basis and everything. You know the dimension of the space is 3. Okay. So dimension of W2 will be equal to 3 minus number of linearly independent constraint. You can apply even this method. So dimension of the vector space is 3, okay, because from R3 they are coming and there is only one constraint. So you get dimension to be 2. So dimension of W2 is also 2. In the same manner, you get dimension of W1 to be 2. Now we want to find out dimension of W1 plus W2. So dimension of W1 plus W2 is nothing but dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. Now we have no idea how to find out dimension directly. So we'll find out dimension of W1 intersection W2. So let me consider W1 intersection W2. So for that, it is saying that W1 intersection W2 means my X1 should satisfy this thing and this thing both. So rather what we will do to find out the dimension of W1 intersection W2, okay, is what? So let us consider, since you are given X1 equal to X2 plus 2X3 and X1 is same as 3X2 plus 2X3, okay. So X1 is X2 plus 2X3 and X1 is also 3X2 plus 2X3. So in that case, what we can to do this, we simply instead of solving this, what I say that it should be true for all. That means that instead of finding this, let's find out the dimension of W2 only. Okay. That will give a clear idea, in fact. So I'll consider W2. It's again collection of X1. X1 is 3X2 plus X3. So instead of X1, we will write down 3X2 plus 2X3. So 3X2 plus 2X3, comma X2, comma X3, such that X2 and X3 are coming from set of reals. So in that manner, what I'll do, I'll take X2 outside and then I'll be getting here 3 and 1, 0 plus X3 times, it will be 2, 0 and 1, such that X2 and X3 belong to set of reals. So it is again a linear span of 3, 1, 0 and 2, 0, 1. And now, if I want dimension of W1 intersection W2, that means I want those elements which are common in both the bases. So L1, it has 1, 1, 0 and 2, 0, 1, and L2, this L has 3, 1, 0 and 2, 0, 1. So these two vectors are common. So that means dimension of W1 intersection W2 is just 1. Cool. Because there is only one vector which is common among them. So now, nicely apply the formula. So dimension of W1 plus W2 will be, dimension of W1 is 2, again dimension of W2 is also 2, minus dimension of W1 intersection W2 is 1. So I get the answer to be 2 plus 2, 4, minus 1 is 3. So the answer would be 3. Okay. Now let's consider this one. So you are given V be a vector space of all polynomials of degree less than or equal to 2. Okay. That means it will be spanned by 1x x square. Okay. With real coefficient, and T is linear transformation given by this. Okay. So let us find the matrix of this first. Because they want the number of non-zero entries in the Jordan canonical form of the matrix T. So first let's find out the matrix and then we'll find out its JC form. Okay, so consider this T of 1, that will give me 2 times 1 plus derivative of 1. So I'll simply go on writing 1 dash. So that will give me just 2. Okay, and T of x would give me 2 times x plus the derivative of x. So that will give me 1 plus 2x. And for T of x square, T of x square will give me 2 times x square plus the derivative of x square. So that will give me 2x plus 2x square. Now write down in their linear combination. So we get 2 times 1 plus 0 times x plus 0 times x square. For this you have 1 times 1 plus 2 times x plus 0 times x square. Here you can get 0 times 1 plus 2 times x plus 2 times x squared. So the matrix corresponding to this transformation would be equal to, write down, go on watching all these coefficients and write down in the transpose wise. So 2, 0, 0, 1, 2, 0, 0, 2, 2. So we got this matrix. Now, if you see this matrix, then the eigenvalues for this matrix, because we want the number of non-zero entries in JC form. So rather I'll find out the eigenvalue of this matrix. Okay. So eigenvalues of TM are, this is an upper triangular matrix, so eigenvalues are 2, 2, 2. That means AM of 2 is 2. Oh, sorry, I wrote it wrong. AM of 2 is 3. Okay, that means AM of 2 is 3. So I just need to check if this matrix is diagonalizable. Okay, so for that I'll find out the GM. So geometric multiplicity of 2 will be equal to 3 minus rank of this matrix. Okay, Tm minus lambda I. Okay, so this is the formula to find out. And now I'll consider this 3 minus rank of this matrix. So that means 2 times identity will be subtracted. So 2 minus 2 will give me 0. 2 minus 2 will be 0. Again, this will be 0. Here you have 0, 2, 0, 0, 1, and 0. The rank of this matrix is 2. So 3 minus 1 equal to 2. That means GM of 2 is 2. And AM of 2 is 3. So this matrix is not diagonalizable, but still it has JC form. Okay, JC form always exists for every square matrix, whether the matrix is diagonalizable or not. So let's find out the JC form. To find out the JC form, we know that AM is always greater than or equal to GM. So if you consider the matrix corresponding to the JC form of this, that means for this, we know that AM of 2 is 3 and GM of 2 is 2. So GM of 2 is 2. That means we want 2 blocks. Okay, 2 JC blocks. There should be 2 JC blocks corresponding to 2. And AM is 3. So we have to break 3 in this form. 2 plus 1. Now there are 2 blocks. One block is for order 2 and another block is for order 1. So it will be 2, 2, 0, 1 and one single block. It will be like this. Okay. Remaining of them will be 0. Well, I guess we made a mistake here just now. If you watch, then I think I wrote it here 1. It is not 1, it's 2. Rank of this matrix is 2. So even this JC form will be wrong then. Let's find out. So the rank of this matrix is 2. So I get GM to be 1. Okay. So I get GM to be 1. Now let us correct the error. So if the GM is 1, okay, GM of 2 is 1 and AM is 3, that means there should be one block. Okay, one block corresponding to GM 2. Eigenvalue 2, for eigenvalue 2 we have only one block, but AM of 2 is 3. So we can have only possibilities that we can have only one block. Okay, GM says that there should be only one block and AM is 3. Okay, so only one block of 3 order. That means JC form will be this: only one block of order 3, because GM of 2 is 1, so it says only one block. Okay, so only one block, but AM is 3, so it should be of order 3. That means 1, 1. Oh, sorry, eigenvalues must be put here first. So it will be 2, 2, 2, and then 1, 1. Now the rest of them will be 0. Okay, so non-zero entries are 5. Okay, so non-zero entries are 5. And now here comes the interesting question from measure theory. Now let's solve this. To find the measure of this thing, you are given that I equals open interval, not open, close to open 3. But anyway, it is an interval. So we will find out its measure by directly subtracting this from this. So I get 3 minus 2, 1. So measure of this interval is 1. Now J is what? Wait, let me write it in fact. So A equal to 2, 3. So measure of I equal to simply 1, because this is an interval of length 1. Okay, from 2 to 3, measure is just 1. So measure of I is 1. And J was set of all rationals in the interval 4 in 4, 6. That means J is collection of all the rationals. That means they want this. Okay. So we know that this is countable. Okay. Rationals are countable. So since rationals are countable, and one strong property of rationals, we know that countable set have measure 0. Okay. So countable set have measure 0. So measure of j will be 0. And k is what? K is the Cantor set. Okay, k is the Cantor set, and Cantor set is again has measure 0. Though it is uncountable, but still see, countable sets have measure 0. But if a set has measure 0, that does not imply that set is countable. It's the counter example. Cantor set is uncountable, but it has measure 0. Okay, and now L is what? Collection of 7 plus x, such that x is coming from the Cantor. So ultimately, if this is coming from Cantor, then this set has measure 0. Then if I add some element into this, still it will have measure 0. So M of L is also 0. Okay, so in that case, I want measure of I union j union L. Okay, so that will be measure of I plus measure of j plus measure of L. That gives me simply 1 plus 0 plus 0, and the measure is 1. So the answer here is the 1. Okay, now let's find out this. You are given u x y z, and they want directional derivative of u in this direction at this point. So to find out the directional derivative, simply apply this formula. So du f of p is nothing but grad f of p, okay, dot u. Okay, so p is the point, u is the unit vector. So first we need to check that is this a unit vector. So 3 by 5 comma minus 4 over 5. Okay. If you take its norm is 1. Fine, it is 1. So norm is 1, that means it is a unit vector. That's perfect. So let us find out. So that means this quantity will be simply del f over del x and del f over del y and del f over del z times use the unit vector, and that is 3 by 5. There is no j component, it will be 0, and it will be minus 4 over 5. Now let us find out. So del f over del x, differentiate this quantity with respect to x, so that we get only 2x. Now do the same thing for y. So we get del f. Instead, I'm using this u. I'll say this is f. Okay. And with respect to y, if I differentiate, I get here minus 2. And with respect to z, I get 4 into 2. So 8z times 3 by 5 over 0 over minus 4 by 5. And now I want this du at this gradient at f of p. So p is 5 comma 0. So 2 times 5, let me write down here, 5 comma 1 comma 0. And minus 2 times 8 into 0. And then you have here 3 by 5 over 0 and minus 4 over 5. So that will give me 5 into 2 is 10. And this is minus 2 and this is 0. And then you have 3 over 5 and 0 and minus 4 over 5. So you get simply 3 by 5 over 10 minus 0 plus 0. So the answer would be 6. So answer is 6. So this answer is 6. Now let's find this Laplace transform. So here you are given that L of y of t is this. Okay. So L of y of t is given to be some phi of s. Then y of t will be given by L inverse of phi of s. So let us find out. Means y of t will be equal to L inverse of this entire quantity, 5 by 2 over s minus 1 minus 2 over s minus 2 and plus 1 by 2 over s minus 3. Now this is distributive, so 5 by 2 will be constant outside completely, so L inverse of 1 over s minus 1 minus 2 times L inverse of 1 over s minus 2 and plus 1 by 2 times L inverse of 1 over s minus 3. Okay, and now note one standard result, that is L inverse of 1 over s minus a is e power at, because the Laplace transform of e power at is 1 over s minus a. So L inverse will be this. Now let us consider. So you get 5 by 2 over e power, this will be simply t, and minus 2 times this will be e power 2t, and plus half will remain, and then it will be e power 3t. So this is my y of t. And now let's differentiate it and find out y dash. That will give me 5 by 2 e power t, and then minus 4 times e power 2t, and plus 3 by 2 times e power 3t. Now we want y of 0 plus y dash 0. Okay, y of 0 plus y dash 0 is what? So y of 0 will give me simply 5 by 2, e power 0 is 1, and minus 2 plus 1 by 2. Okay, and y dash of 0 will be, let's add, so we get again 5 by 2 minus 4 and plus 3 by 2. Now simply add them. Okay, so y of 0 plus y dash of 0 will give me 5 by 2 plus 5 by 2 will give me 2 times 5 by 2, and minus 2 minus 4 and plus 4 over 2 will make it 2 and 2 get cancelled, 2 and 2 get cancelled, plus 2 minus 2 will get. Once again, did I make any mistake? Yeah, 5 I did not count, so 5 minus 4 will give me 1. So the answer is 1. Sorry. Now let's find this one. So you have given the number of regular singular points of the differential equation in this interval. So in this interval, you have to find out the number of regular singular points. So let's find out the number of regular singular point, RSP. And the best way to find out the solution is first compare in this form. Y double dash plus P of X times Y dash plus Q of X into Y equal to 0. So to find out the RSP, I'll say RSP, it is a regular singular point. So first you need to find out this capital P, which is equal to limit X tends to X naught, okay, the regular singular point which you feel, okay, times X minus X naught into this P of X. This limit should exist finitely, and Q is, wait, small p, this is capital, small p is capital. Limit X tends to X naught, so here you have X minus X naught square times Q of X. Even this limit should exist finitely. If both the limit exist finitely, then we say that, okay, X naught is a regular singular point. Okay, so here we have got two things. Okay, so here we have to check X equal to 0 is a problem because it will make this quantity 0, and X equal to 1 is a problem. So let us first write in this manner: cos X into sine of X minus 1 over X minus 1 square into sine X into Y dash plus, I'll erase it, this part, which will occupy the space. In case you buy a bullet, then please make sure that its sound is quite less. Okay. Plus cos X into, oh sorry, this distracted everything. Okay, and plus X minus 1 over, it is X minus 1 square times sine of X to Y equal to 0. Now this quantity right here is my P, this is my Q. Okay, now let us find out and see. P is becoming 0 at X equal to 1 and 0. So first we will check at X equal to 0. So at X equal to 0, we need to find out small p, and that is limit X tends to 0. So X times capital P of X. So that will give me limit X tends to 0. You have here X, and what is P of X? It's simply cos X into sine of X minus 1 over X minus 1 square into sine X. Now nobody is causing me the trouble except this X over sine X. So that will give me 1, and this quantity has nothing to do with 0. So this limit is finite. Okay. Or in case you are wondering, then I'll write down sine X here. Okay. This limit is 1. We don't have to worry with this limit. This is 1, and then sine of -1 over -1 square. So this is finite. Okay, this is what I meant. And now I need to find out q also. So q will be limit x tends to 0, x square into p of x, and it will make it x tends to 0, x square. So x square into x minus 1 over x minus 1 square into sine x. Now this x minus 1 and this x minus will get cancelled, and this is x square. So rather I'll write it x into x, so that this limit becomes 1, and limit x tends to 0, x over x minus 1 will be 0, which is clearly finite. So from this two I can conclude that x equal to 0 is a regular singular point. Okay, suppose if any of the limit fails to exist, then I'll say that x equal to 0 is an irregular singular point, IR. Okay, now the same thing that we have to do is with the q. Okay, so we got one regular singular point, 0 is an RSP. Now let's do everything at x equal to 1. Okay, so let's play the game at x equal to 1. So I'll now erase and find out the same limit at x equals to 1. Oh, only thing that will change is this. Now I'll have different story. So it is x minus 1. Okay, so I'm playing the game now at x equal to 1. So this will be x minus 1 square p of x, and here I'll be getting here x minus 1. Okay, and here again it will be x minus 1 square. So let us find out this limit first, and then we will solve further. Yeah, so you got limit x tends to 1, x minus 1 into p of x. So I have limit x tends to 1, x minus 1 upon this entire quantity. So this x minus 1, this x minus 1 will get cancelled, and sine of x minus 1 upon x minus 1. As x tends to 1, this quantity becomes 0. So it is sine x over x, which will give me 1. And cos upon sine will give me cot. So it is simply cot 1. Okay, which is again finite. And now if you consider q, then limit x tends to 1, x minus 1 square into, this is q of x. Okay, it's q of x. So q of x is this quantity right here, x minus 1 upon s square. So this x minus 1 and this gets cancelled. Okay, and once again, and this x minus 1 and this 1 x minus 1 will get cancelled, and x tends to 1, this sine x has nothing to do with 1, and this numerator becomes 0. So this is again finite. So x equal to 1 is also 0 and 1 are RSP. And let's check if they belong to this interval 0 to pi by 2. We have 0 also, and 1 is also inside, because pi by 2 is less than, pi by 2 is greater than 1. So 1 is inside. So there are 2 RSPs inside this. Okay, now let's solve question number 20. Okay, this is obvious and quite easy. So let f be a field of 7 power 6 element. Okay, so cardinality of f is 7 to the power 6. Okay, and k be a subfield. Okay, so k is a subfield with 49 elements, so that is 7 power 2. Okay, then the dimension of f. Okay, so there is simple formula to calculate the dimension. Okay, it's simply, if you have field of cardinality, say p power n, and a subfield of cardinality p power k, and you want dimension of f over k, then it is simply n over k. So what is n here? 6, and k is 2. So the answer would be 3. Okay, in that case answer would be 3. So in this part 1 we will solve 20 questions, and remaining questions will be solved in part 2. Thanks for watching.